Our last lesson this week from section 4.6 tells us how to use the method of variation of parameters to solve non-homogeneous equations, specifically in cases where the method of undetermined coefficients won't work. If you think back to our lesson on undetermined coefficients, the idea was that we had some specific function on the right-hand side that helped us make a guess at what a particular solution might look like. So if that right-hand side is something involving, say, an exponential function, a polynomial, or sines or cosines, then based on that lesson on undetermined coefficients, we can make a pretty good guess at what a solution might be, plug it into the equation, and find those coefficients that make it work. And after finding a particular solution that works, we know how to find the general solution as well. The general solution is the same thing I have written down here at the bottom. It's just a combination of your homogeneous solution and whatever particular solution you found with undetermined coefficients. The problem with undetermined coefficients is that it won't always work. If that right-hand side function f of t doesn't fit one of those basic categories of exponential, polynomial, or sine or cosine, then we may not be able to make an educated guess of what a particular solution might look like. So in that case, we're going to need a different approach. This is where variation of parameters will help us. Just like most things in math, the methods that we're talking about here have their advantages and disadvantages. Undetermined coefficients, its advantage is that it works pretty easily. Its disadvantage, though, is that it won't always work. Again, if that right-hand side isn't one of those special types of functions, then we just can't use it. On the other hand, what we're going to see in this section with variation of parameters, this is a method that should always give you a solution. The disadvantage to it is that it may take a little bit more work than undetermined coefficients did. Really, though, variation of parameters isn't too bad because it's going to boil down to just doing two integrals. If you can do two integrals that I'll show you in a minute, then you'll be able to write down your answer. Just to summarize the process of variation of parameters, the way this will work is you'll start by solving the homogeneous equation. So the corresponding homogeneous equation, ay double prime plus by prime plus cy equals 0. We already know how to solve those. You get your auxiliary equation, and the roots of the auxiliary equation tell you what your solution should look like. If you have two distinct roots, then y1 and y2 will be exponential functions. If you have two repeated real roots, then y1 would be, say, an exponential, and then y2 would be t times that exponential function. And then, as we've seen, if you have complex roots, then y1 and y2 could be some combination of exponential functions, sines, and cosines. So we already know how to solve homogeneous equations, and this first step should be pretty straightforward for us. Once we solve the homogeneous equation, we're going to need these two pieces that we found, the y1 and y2, those two functions that we got in step 1, we're going to need them in step 2. In step 2, we're finding a particular solution. Okay, this is where our method of undetermined coefficients usually gives us a particular solution, but if we're in one of these cases where undetermined coefficients won't work for us, we'll need to use this method instead. Our particular solution is going to look like this. It's going to be v1y1 plus v2y2, where y1 and y2 are exactly what we found in step 1. So then all that's left is we need to figure out some function v1 and v2 to attach to those. Now we have a specific formula for v1 and v2 that I'll show you in just a second, and this is where the integrals will come in. Once we've found our homogeneous solution in step 1, and once we've found our particular solution in step 2, step 3 is no different from what we've seen before. Our final answer, our general solution to the differential equation, is a combination of the two, the homogeneous solution plus the particular solution. Alright, so really the only new thing here in this process of variation of parameters is we haven't talked about how to find v1 and v2. So let me show you the integrals that you'll use to find v1 and v2. Now, if I had time, I would go through an explanation about where these integrals come from, but here I think I'm just going to go straight to the formulas themselves, and your textbook on page 188 gives a pretty in-depth explanation of where these integrals come from, if you'd like to read there. v1 is the following integral. It's negative f times y2 divided by a times y1, y2 prime minus y1 prime times y2. So there's a lot going on in this integral, but the thing you need to understand is really all the pieces here are pieces that just come from work we've already done or were given to us in the equation. So for example, this f is exactly what we had on the right hand side of our equation. Everywhere we see a y1 and a y2, those again came from step 1 in our process when we found our homogeneous solution. A is the number attached to y double prime. Okay, so we have a y double prime. That coefficient a is the number that goes right here. Now, in most cases in your homework, this integral, even though it looks like it has a lot going on, there's going to be a lot of cancellation and simplification, so it turns into an integral that's really not that bad. v2 is another integral. This integral will look fairly similar. In fact, the entire numerator is exactly the same as what we had. Sorry, the entire denominator is exactly the same as what we had in the previous integral. A times y1, y2 prime minus y1 prime times y2. That's no different from the denominator for the integral in v1. The only thing that changes is on top, instead of a negative f, I have positive f. And instead of y2, I have a y1. Now again, I'd love to go into an explanation of where these integrals come from, but bottom line is we just need to put all the pieces where they belong and get our answer. So once we do these two integrals and find v1 and v2, then we have all the pieces we need to write down a particular solution. The particular solution will be v1 times y1 plus v2 times y2. And once I have my particular solution, then I have everything I need to write down my general solution, which is a combination of the homogeneous and the particular solution, yh plus yp. Let me run through one quick example with you. So we're going to solve y double prime plus y equals tangent t. Now notice the right hand side here, tangent t. That's not one of our basic functions we could do where we could use undetermined coefficients. If it's sines or cosines, yes, we can handle it with undetermined coefficients, but tangent doesn't fall into that category. This interval negative pi over 2 to positive pi over 2, don't worry too much about that right now. Part of the reason for that interval is we're looking for some interval where tangent is continuous and tangent is continuous on that interval. And it'll also work out later. There will be an absolute value that can go away based on the fact that we're dealing with this interval. All right, so don't get hung up on the interval. Let's just focus on the going through the process. So the process, again, step one is to solve your homogeneous equation. Alright, so in step one, my homogeneous equation is y double prime plus y equals 0. I'm replacing the tangent t with a 0, and now I have a homogeneous equation. To solve a homogeneous equation, we know how to do this. We start with our auxiliary equation. The corresponding auxiliary equation is r squared plus 1 equals 0. This one's fairly straightforward to solve. We get plus or minus I. If r equals plus or minus I, that's a complex root to our auxiliary equation. So we know that our homogeneous solution will be e to the alpha t sine beta t and e to the alpha t cosine beta t. It'll be a combination of those two. But in this case, our alpha is 0 and our beta is 1. So I can say that y sub h equals e to the 0t, which is just 1, so I don't even need to write that, times sine beta t. So I've got c1 sine beta t, sine 1t I should say, plus c2 e to the alpha t, which in this case, again, e to the 0 is just 1, cosine beta t. Beta is 1, so this is just cosine t. So our homogeneous equation has the solution c1 sine t plus c2 cosine t. So in this case, these two functions right here, sine and cosine, are the y1 and y2 that we're going to need in the next step. If you look back at the formulas, we'll also need y1 prime and y2 prime. So let's go ahead and do that real quick. y1 prime is cosine, y2 prime is negative sine. So looking back at your formulas, v1 is the integral of negative f times y2, and in this case f is the tangent function, so negative tangent t times y2, which in this case is cosine, divided by a. Remember, a was our coefficient on y double prime. In this case, a is 1. So we have 1 times y1, which is sine t, times y2 prime, that's negative sine t. So really I'm just going to end up with a negative sine squared t, minus y1 prime, that's cosine, times y2, that's also cosine, so minus cosine squared. So in this case, the whole thing in the denominator, that a times y1, y2 prime minus y1 prime, y2, it's actually going to simplify quite nicely, because if I factor a negative sign out, or cancel with the negative sign that I have on top, I have sine squared t plus cosine squared t on bottom, which is just 1. So this integral is going to simplify to tangent t times cosine t, and some more basic trig identities. Tangent is sine divided by cosine. Sine divided by cosine times cosine. The cosines will cancel, and this simplifies down to a really easy integral, the integral of sine t. So then our our v1 would be negative cosine t. And I'll just throw on a constant here. Now, one thing I'll mention is right now we're trying to find a particular solution. This v1 will work no matter what constant we have here. So these integrating constants, we're going to just choose 0. Alright, so since this will work for any constant, we will choose C1 equals 0. So really we have v1 is the negative cosine function. v2, you just go through this integral again, but the numerator changes. The denominator is exactly the same, so we'd still end up with sine squared plus cosine squared in the bottom. But in the top, I have f times y1. F is still tangent t. But now y1 is sine t. And the bottom doesn't change. We still have sine squared plus cosine squared, so really that's just going to simplify to 1. So for v2, we're doing the integral of tangent times sine tangent t times sine t. Now, this integral is a little bit uglier, and I'm not going to go into integration techniques right here. They give a little bit more detail in the book on page 189. I'm just working example 1. So if you want to look and see a little bit more detail in the book, you can. But the goal here isn't to do a whole lesson on integration techniques. The goal here is to show you how the method of variation of parameters works. So bottom line, after doing the integral, for this one we're going to get sine t minus natural log secant plus tangent. And again, we would have an arbitrary constant there, but since this will work for any constant, we're just going to choose 0 for simplicity. So v1 is this cosine function, v2 is this ugly function here, sine t minus natural log secant t plus tangent t. I'll also mention originally the natural log has absolute values on its argument, but that absolute value goes away when you realize that we're dealing with this interval negative pi over 2 to pi over 2. Secant t plus tangent t is always positive on the interval, so the absolute values won't be necessary. So after doing all that work, we found yp is going to be v1 y1 plus v2 y2, where v1 and v2 are the two pieces we got from these two integrals. Y1 and y2 were what we found in that first step. And then finally, you just put everything together to write down your final solution. The function we had here for yh on the left goes in place of yh for our final solution, and then all this big mess that we got for our particular solution goes in place of yp. Once we fill those in where they belong, we have our final answer.